All righty. Thank you all the folks who have decided and continue our interesting discussions about spectral processing. I will go through a few additional examples of non-uniform reconstruction. And then if there are some brave folks in the audience, we can invite one or two people, share their screens, and can reproduce some of the things that we've seen in this software. And if anyone has questions, please call them out. So when we left off, we had Fourier processed this 3D data set, and we're looking at planes and at 2D projections, and this interface also has a button that will let us generate 3D strips to get an overview of the data. And this is a nice function. One, the way this function works is that it takes a 2D projection of the data, performs peak detection on that 2D projection, and then at the position of every 2D peak that it finds, it draws a pair of strips in this graphic. In this case, one strip is along the proton dimension, and the other strip is along the nitrogen dimension in the short axis, and both strips are along the carbon dimension in the long axis of this display. So what this strip plot allows us to do is see what the peak profiles look like throughout the entire spectrum. So this lets us see that the data is phase corrected well in all places. It lets us see what the line shapes look like in all the dimensions. And we can do some other fun things with this interface. We can move these slices around. If I click on the slice label, I can adjust the contour levels for that slice with the mouse, changing the scroll wheel. So very handy. And we can do some other useful things in that way too. So this was a regular Fourier reconstruction of this 3D data. But let's say instead that we wanted to include linear prediction extrapolation. And so in the processing interface, I've turned on those checkboxes. And now I'll generate a new script and execute that script. When we use linear prediction on a 3D data set, whenever we apply linear prediction to one particular dimension, we'd like the other two dimensions to be Fourier transformed already. Because as we discussed earlier on, when you Fourier transform a dimension, you concentrate the signals into particular locations and make the remainder of the spectrum more empty of signals. And so when you do that, it becomes easier to linear predict the spectra because different spectral regions have fewer signals in them when the other dimensions are Fourier transformed. So when we use a linear prediction scheme on a three-dimensional data set, we do it in an indirect way. We process two dimensions, linear predict and process the third dimension, and then go back, inverse process, linear predict, and reprocess the intermediate dimension. It's a rather complicated processing scheme, but the interface builds it for us automatically.
So Frank,
yes.
So In the last panel, so the exchange Y and Z axis, you're provided like a manual choice there. Where do you normally use?
That's a good question. So let's say you had an N15 NOE experiment.
Okay.
It was measured so that the first two dimensions are proton and nitrogen.
Right.
And the remaining dimension were proton. But
Right.
maybe it's more convenient when the final result are proton-proton planes instead.
Right.
So that would be a case where it's handy to exchange the y-axis and the z-axis.
Oh, this is just the display part, not anything to do with the processing.
Well, it also changes the processing because it rearranges the spectrum in a different order.
Okay.
So now we have a linear prediction result, and if we draw strips this time, we can see both our previous regular Fourier transform result and see that side by side with our new linear prediction result.
Oh, that's cool.
And you can obviously see that the signals are narrower now, so that's pretty handy. And then finally, really quick, instead of using linear prediction to extrapolate this data, let's try SMILE instead. So I'll select SMILE from the extrapolation menu down at the bottom, and then create a new script and execute it. Here's the SMILE part of the calculation. It took 3 seconds. So it's actually faster than the linear prediction. And now we have the SMILE result. And if we draw strips this time, now we have our beautiful results side by side, the Fourier transform, linear prediction, and SMILE. So super easy not only to conduct this processing, but to compare the results. And so finally, let's do the same sort of thing with an actual non-uniformly sampled data set. When we convert non-uniformly sampled data, the details are the same, except that the interface now, in addition to needing input about the spectrometer data, also needs an input with the non-uniform sampling schedule. And the corresponding conversion script that gets created takes the raw spectrometer data and sorts it and expands it to fill in the empty spaces that were skipped during the acquisition with zeros. So let's look at that and see what it actually means. So here's NMR draw now in the non-uniform sampling reconstruction mode for 3D data. We have a bunch of new commands up at the top, but the spectral processing details are pretty much the same as we saw before. A set of parameters for each of the 3 dimensions. And down at the bottom, a choice of which reconstruction methods we're going to use for the data. So just as I mentioned before, the recommended workflow for non-uniformly sampled data is to first just generate an ordinary Fourier transform scheme and execute it. So I'm going to do that. No phase corrections or any other parameters. And here's some planes from the data. We can look at the XY projection, and that's actually looks pretty good to me, except that it's not phased. And we look at the XY projection, XZ projection. Now the XZ projection is flipped. The two edges are flipped like we saw before. So what should be the center of the spectrum is at the edges. So I'll go over here to the interface and say rotate the two halves of the data. And I'll update the script and execute it again. And now if I look at the XY, what did I do?
Frank, you rotated Y instead of Z.
And isn't that what I want to do? They both need to be rotated. All right, let me start again. So XY, okay, XY is okay. XZ is the one that's rotated. Thank you, sorry. So I will do that and update the scripts. And now execute our FT. So the XY projection looks okay in terms of where the peaks are. The XZ projection, now when I look at this, let's see. This dimension is supposed to be H alpha, H beta, right? But all the peaks are down here around 7 or 8 ppm. So not only was this data have the center rotated to the edges, but it's also reversed.
Right.
So I will check the checkbox that will fix that, and we'll update this script. And now execute an FT. And now the XY projection looks pretty nice, and the XZ projection also looks pretty good. And now all we have to do is phase correct the directly detected dimension properly. So in order for the auto phasing to work properly, it's best if the other parameters about the indirect dimensions are set up properly, because the auto phasing will be done based on the signals towards the center of the spectrum. And so if the signals are rotated to the edges, the phase correction won't work quite as well. Anyway, let's turn on auto phase correction and update this script and see how it goes.
Hey, Frank, Jeff here. This is a non sequitur, but have you ever tried Sierra for solvent suppression?
That won't work.
Thank you. It's a doubly selective suppression technique that needs a proton and a carbon.
It's an HX tool.
Well, I was thinking more of the processing, the fitting side.
Oh, I suppose you could use a SMILE signal model as a way to subtract solvent signals. Yeah, that is within the realm of the possible. Haven't tried it. It's a good idea. I'll keep it in mind. Anyway, so we have our process result. Here's the XY projection. Here's the XZ projection. Everything looks pretty good. So now we're ready to do a NUS reconstruction. And you see there were several parameters that we had to get straight before we did that. So that's why we recommend doing a regular Fourier transform scheme first. So let's, in the interest of time, choose SMILE as our first example. Now update the scripts accordingly, and now execute the non-uniform sampling reconstruction for our data.
So Frank,
Yeah.
the scheduling file is read at the conversion stage, and at that point you've expanded and zero filled or whatever. Let's just say expanded the file, so you don't need
Yes.
that
Yeah.
anymore. Once you've gone through conversion, then it's just whichever reconstruction tool you want to.
Exactly. So when this processing is finished, I'll actually point out one or two details about this. If you look in the interface, you'll see that we have buttons to show the Fourier transform data, but also show the time domain data and show what we call the non-uniform sampling mask. Okay, so I'll display that in a bit. The smile reconstruction is finished. That part took 7 seconds. Now the remainder of the data is being Fourier transformed.
Yeah, there's got to be something illegal happening in there, Frank.
All right, so here's planes from our smile reconstruction, but let's look at the strips. And they're beautiful. Wow, they're just gorgeous. So that's all it took. Now to step backward to Andy's point, so we could look at the time domain data, and if you look at other planes in the time domain data, you can see where the gaps are, right? When we convert NUS data in NMR pipe, in addition to creating this expanded time domain version of the data, we also create a mask. So the mask is a copy of the time domain data, but it contains only zeros and ones. Has zeros where data was skipped during the NUS measurement and ones where data was kept. So you can take this mask and Fourier process it just like a spectrum in whatever way you use time domain data to generate a point spread function. Or you can multiply this mask by a conventional FID to generate non-uniformly sampled data. And that's how we resample data in NMR pipe. So very convenient. Anyway, so that was a smile reconstruction. Let's do a Nesta reconstruction next.
That might be cruel.
No, maybe not. I actually don't think so. I think the results are quick and pretty nice.
It's nice to see it run, though. Thank you. I mean, it runs here too, but it's nice to see it run in box. That's very cool.
10 seconds, 18 seconds, not bad, huh?
Yeah,
So,
not bad, not bad. I'll take that.
if I use my IST, it'll probably take 15 minutes. So it's
That's
very
right.
good.
That just reminds some of us about how slow processing used to be.
Okay, so we got our planes, blah, blah, blah. Let's look at the strips. See, beautiful. So there's the
Not
smile.
bad.
There's
That's
the
cool.
result. Yeah, and it didn't take long. And you see, once we've established the parameters of Fourier transform and phase correction, it's trivial for us to move between one method and another.
Yeah, that's a really nice example of your workflow. You guys have done great. That's cool. That's really nice.
Yeah, thank you.
That's really nice.
So Frank,
Yes.
so the strip transform therefore compares let's say the peaks which are from a regular Fourier transform vis-a-vis the Nuss method, correct? So
In this case, it's the Nuss
Thanks.
data reconstructed by two different methods.
right. Okay. So it side by side compares it as you showed us on the screen there. You said it does an automatic picking to do this, correct?
Yes.
So is this method, is there a way it can kind of eliminate false positives when by by an eyeball examination? When I look at this, is there a way I can say, okay, in the low resolution FT, it looks like this, but then with the reconstruction with two different methods, let's say, I do not see a couple of peaks appearing. So then this must be a false positive. Is that kind of a reasoning
Yeah,
useful?
that's part of the reason that we have these results side by side, and so
Yeah.
you can inspect them. You could see if one particular sampling schedule or one particular reconstruction method tends to leave out peaks that you would see in a different reconstruction or with a different sampling schedule. So yes, that's one of the purposes of this particular interface,
Okay.
to
Yeah.
let you evaluate the quality of the result with respect to reconstruction method and with respect to the sampling schedule that you use. And in this interface, as we change from one reconstruction method to another, the output name is changed automatically,
Okay.
but you can change it yourself. So you can save as many of these results as you want with slightly different parameters, different sampling schedules, and then be able to view them all together side by side.
Okay.
So that is my overview of non-uniform sampling reconstruction. Are there any additional questions before we go on? Very good. Now, I want to ask for one brave volunteer who's able to log in to NMR Box and to share their screen. And the volunteer will be called upon to go to one of these demo directories and reproduce some of the steps in the examples that we've seen. So I see one person has raised their hand. I don't know if it's because they're volunteering or because they want to tell me to shut up. Maybe you can unmute yourself and say so.
Yeah,
Well,
I'll
I
give it a
think
try.
I asked my share of a lot of questions today. I will hold the fort.
Okay, Robert, I see that you've raised your hand. Do you have a comment or are you volunteering? And unmute your mic to reply.
I was volunteering. Sorry, the press space thing works unless your cursor is in the chat window and then it binds to that and
Understood.
never lets it go. Anyway, okay, yeah, I can try.
Okay, very good. Thank you. I'm grateful that we have a volunteer. So let's see, what do we do?
I will share.
Do you have the ability to share your screen?
Not while you are sharing your screen. Okay. In that case, then yes. It's like I can do that.
Okay. Very good. And I wonder, let's see what else. Do I have a way to request control of your mouse
There is a
and
button.
keyboard?
There is a button for that somewhere.
Yes, I'm
Let
looking.
me jump in
Oh,
because Frank, you switched me up, but we'll go right away. Robert, on the top right where it says VNC next to your name,
Yep.
click on that. Then in the menu next to the little one, yep, do options. And then there's user and permissions. Yep.
Lets me.
And maybe you have to close that box. Yeah.
Sorry, yeah. There we go.
Okay, now click add.
Add.
And we'll make this easy. Do group,
All right.
then type NMR box, all lowercase, 20. And then okay. And yeah, you should be able to hit okay there.
Yeah.
But before you close that, so Frank, do you see the IP and port?
I do. So I will connect to that right now. Let's see.
Yeah.
155.37.253.123:5. Boing.
Okay. And Robert, you should be getting a prompt that you have to you might get a prompt to allow Frank in.
Sure.
All right. Oh, I like this.
It didn't prompt me, it just let it happen. All right, great. There we are.
Okay. So this is me wiggling the mouse.
I see. You have 2 different mouse cursors. Or
Oh, wow. That's fancy. All right. So this we can ditch. And I will do this. And I'm going to start you off by copying the course data to the Scratch partition for you. Well, actually, you have to do it. So I will let you do it. Oh, wait a minute. No, I'm you. It's great. What could be better?
Slash, yeah.
yeah, slash Scratch. There.
Okay.
Oh, that's annoying.
Okay, let's see.
Sudo.
Looks like it's
Sudo
just
copy.
one directory. Just one directory. All right, we won't worry about it for right now because we're not going to look at that one. Okay, so for those of you who are using NMR pipe on NMR box, the first thing to do with every window is start a C shell.
Right, of course.
H. NMR pipe has to be operated from the C shell. Okay, so there we are. And let's have a look at the 2D data set that we worked with at first. It's in the directory
GB3. Yep.
You can type ls to see what's in there. And
here we are.
all of these demo directories have a script called clean.com that you can execute that will erase any previous results that are there.
Wait, sorry, I just wanted to see what it is.
Yeah, sure thing.
Okay, yeah, so it deletes a bunch of stuff. All right.
Exactly, cool. That's all it does. And all of these directories will have a script called all.com that happens to go through the different steps of a demo, which in this case means delete the previous data, execute a conversion script, execute a processing script, and take a look at the results. So let's do these steps by hand. So the first thing to do is we're going to pretend this is raw data we've never seen before. So our first stage is to construct a conversion script.
Right. So
this is
Bruker data. Yeah.
Exactly.
So I want to do
Bruker. Very good.
And as we saw before, it was from file. We want to go input Bruker, output NMR pipe, read as many parameters as possible, output it with some sort of template. Read. These look like relatively normal numbers.
Right. And let's check the button that says run NMR draw in process mode.
Ah, yes, that's right.
Conversion.
Information and temperature. Yeah, okay, great.
And now execute the script. Save the script and execute it.
Save. Overwrite. Yeah, sure.
Okay. And it looks like your screen resolution is kind of low. We might.
Yeah, it's because it's on my, oh, sorry. It's just because it's on my laptop.
Uh-huh. All
Yeah.
right. I guess
We'll do our best. I could
it's
put it on
even
my other
better.
monitor, but
Yeah.
if I need to.
All right.
All right. We can get really used to all of these scroll bars. It's amazing. Right. So we have the data here. It has the usual shape where you have the Brooker filter delay at the beginning, all
Yes.
that good stuff.
The mouse menu is where you can look at.
That's what I was looking at.
Yeah.
I don't want to do both. Yeah. So we have the usual.
All right. And if you move the mouse to the axis and use the scroll wheel, you can change the contour levels.
Right. That's right. Yeah. That's the contour level.
Very good.
Yeah. Very good.
And you might notice when you open up one of those menus, like the mouse menu, every command has a one-letter abbreviation.
Yeah.
So as an alternative to using the menu, you could just type that command at the screen.
Yeah.
And one of the most useful ones is that exit command.
Yep, the one I just did.
Off the mouse.
Yeah.
Okay, so let's go over to the script side of things and just update the script and execute it.
Let's read it.
Or you can read it. Yeah, you take a look and see what it looks like.
Looks like solvent suppression, appetization, zero fill Fourier transform, phase correction that does nothing, extractor region, transpose, appetization, zero fill Fourier transform, phase thing, transpose again, baseline correction, I guess.
Yes.
That's what it's doing, right? Yeah.
Right. So since the script generator recognized that this is amide detected data, it put in a solvent filter, extracted the left side of the data, and also included a baseline correction.
That's very nice.
That's automatic.
Very nice. All right. So done with that. So let's execute it.
Yep.
And now we have this. And now let's do these again because it's fun. And we've got lots of nice peaks that are not at all phased.
Right.
In particular, we have this one, which is, again, not at all phased. Well, that's not true. It's they're not at all phased in the direct dimension.
Yes. Right.
They're phased just fine in the indirect dimension,
Right.
which I guess makes sense because really I should only have to do this once. So I need to now start playing with this, and that gives me the ability to, see what's happening here. It's filling in the information.
Right.
This is a fine adjustment. Yes, it is. And that looks pretty good. Here, look at a different peak. Yeah, that's good enough, probably. Yes. Let's see how this is. Maybe there's a little teeny bit of 1D that would need to be applied. I have no idea. But obviously there's stuff that one could do. Many.
Right.
Yeah, so I can play with that manually forever, or I could.
Yeah, right. That too.
Or I could hit auto.
Yep.
And actually, that's nice. Now you can do. I can show fit or show FT. I can. Oh dear God. Okay. Too much mouse wheel. All right. Wrong way. Wrong way. I am sorry, Anna Mardraw. I did not want you to do that, but let's zoom you out to a point where you can actually see things. Yes. So now if we update it, and then that should have an auto in the auto phase somewhere. Yep, it does auto phase, and then it puts that in here, right?
Very good.
And we execute it.
You're a master. I didn't need to show up today.
Great. It's. I had to decipher these.
Careful, Frank. We may recruit him for the next workshop.
I think that's an excellent idea. Okay, so beautifully phased. Now what else do we have to change?
Right. Now we have, I just wanted to check again just to be sure. Yeah, okay, everything looks great. What is that? Okay, so now we have, okay, yeah, as you said, the y-axis is not centered.
Right.
And this is something that, yeah, I mean, you hopefully set your experiment so that your data is not at the edge of your spectral window. So that would be, so it's likely that that box needs to be checked. That's better. I mean, I guess you could set it so that it's at the edge, but no, that doesn't make any sense because it'd be really weird spectrum to actually look like that naturally. I guess it's not impossible. And then, yeah, so we can try y-axis linear prediction. No, let's just do it. I have no idea how much it'll change, except that it'll take longer. All right, everything gets a little smaller.
Yep.
Yeah. And then could undo that and could do, say, smile, NUS style extrapolation, and then update, which now has a smile function somewhere. Yeah, there it is. It's right here, where it does the smile in it. We run it.
Fabulous.
And it looks very nice.
It does
Right.
indeed.
Yeah.
So congratulations.
Yay. Yeah, and then similarly for the NUS data, I would follow a similar workflow to the one that you showed just before this, right?
Yeah, that's exactly
All
right.
Great. Makes me feel a lot more confident in using this.
Okay,
It's a lot
super.
easier to use this program on NMR Box than it is on my Mac at home because
NMR box is fabulous.
it's
in
Linux
every way.
and it just is. It feels like it's a little bit more. I think my computer doesn't like NMR draw very much or something.
No,
Not
Mac
sure.
Mac hates NMR draw.
Yeah, it gets really confused.
Okay, Robert,
Okay.
you're definitely coming to future workshops with praise like that and demo abilities.
Oh, thanks.
Frank,
I'll stop
so
my share now.
if you have NUS data, does the conversion automatically, if you have NUS data, you do the conversion, you get the file, and then when you say start up in process mode, it automatically fills the menu in. Is that correct?
Yeah, so let's look at an
Okay.
example like that. We have one. So NUS 2D. All right, so this
You're going to have to
is,
share again.
okay. Robert, do you want to keep sharing and doing this? Did we lose Robert?
Here he is.
No, I just remuted my mic and just forgot.
Oh, okay.
Okay. So what was the question again?
This is a
Okay.
2D NUS example.
Right.
So I wonder if you wouldn't mind going through the same kind of steps, but for this data, so
Okay.
that Andy can see again how the conversion differs.
Right. So this is again a Bruker file.
Yeah.
And this schedule says NUS list, which theoretically exists in here. Yeah, there is a folder called NUS
Yeah,
list.
so it's
or a
so
file.
you automatically look for that, Frank. When
Exactly.
when
Yeah.
Brooker runs, it looks for those sampling schedules and stuff like that. Okay.
That's
And I
correct.
assume,
So
and I assume that that is because it that's because it
But probably knows in the Brooker file the sampling
that's-
mode.
yeah, I guess
The
that's
FN mode,
that's,
it's already done that. So
yeah, and that's the default Bruker file name for the NUS list, I guess. So
correct.
would be my guess. All right. So this looks cool. It's got echo, anti-echo, DQD, a bunch of numbers. Save it.
Here's a rhetorical question, and Andy is not allowed to answer it. Does anybody know why that sign alternation still lingers in some Brooker data?
I hate this. I hate this problem. Sorry. I don't know why, and I would love to know why.
So it's a historical artifact back in the days before four-phase shifters, 0, 90, 180, 270 were available. And Al Redfield was the guy, I think it may have been Al Redfield who first figured out.
it was Al, absolutely.
Yeah, that if you had a 0 and 90 degrees phase shifter and you alternated the sign of alternate points, that you could mimic a four-phase box out of a two-phase using a two-phase shifter.
Yep, it
Yeah,
was
I guess
actually written in the source code, the Redfield trick.
Yes.
in the source code of both Brooker and Nicolay. It was actually Dave Dalrymple that wrote the Nicolay software and had it in there. But
And
it was
so
Al
so
that figured it
so
out.
where it came from is the easy. We know where it came from. What is the imponderable is, why is it still there?
Oh God, you
Technical
got to go to
debt.
Brooker for that, baby. You got to go to Brooker for that.
Tech debt. That's probably why. Okay, execute the Fourier transform. We see something gross. That doesn't look right. Which is fine. I guess it's just a phasing issue. Because yeah, this is fine. It's just the vertical axis has a big weird phase.
Right. And
Of course,
so
there's a huge number, and it's a giant mess anyway, because I have no idea what the spectrum is actually supposed to look like.
this
So-
data is gradient enhanced.
Mhm.
And gradient enhanced data, when it's converted in NMR pipe, often requires a 90-degree phase correction in that dimension.
Right.
So when you see data like this, you could just stick in a 90-degree correction and see
Right.
what it looks like.
Does it matter which dimension I put that?
Yes, it's a 90-degree correction
Yeah,
in,
of course.
in the indirect dimension. In the
Yeah, of
carbon.
course. So execute it. Yeah, oh, that's much better. Okay, so now we have some stuff that looks suspiciously like artifacts and a big blob and a line. All right,
Right.
That's probably what we want. Yeah, that looks a little better.
Okay, it's not phased yet in the proton dimension.
No, it is not. It is, but I need to find something that, yeah, I want to find something that I can look at it to, I mean, I could click auto, but I also just want to find something where I can actually see well enough to phase it, or to at least play with it. When this
Okay.
is kind of hard to do.
One thing that might help if
Yeah, that's
we
probably very good.
either zoom on this or reprocess it with a narrower chemical shift window.
Yeah, that's true. I mean, this is probably fine. So there is, in fact, I don't know, there's something going on here. AKA, there is probably a first order phase issue, because I can't get that little peak, because it's at like 4.5, to be absorptive and keep the big blob at 1 absorptive. So
Right. So that peak at 4.5 is a leftover solvent, so it can't be.
yeah. Okay.
So I
So
would
I
say
should-
this is probably as close as you could get.
All right. So that's pretty close. In that case, I'm just gonna click auto.
Oh, that'll work too.
Yeah, because it's like, okay, well, this is 14. It's not going to be very much. Let's just execute, and maybe it'll actually tell me what it did. And then I can check it. It should. I think it does fill in it afterwards. Yeah,
Yeah,
16.
it
That's
does.
fine. All right. So,
Let's reduce the proton chemical shift window.
yep. All right. So,
You could see their parameters for region start and end.
oh, yeah. So we need to do, so say 3.5 to, yeah, 3.5 to -1.
That sounds good.
Sure. Yeah, looks good.
All
It
right.
does.
Yeah.
So now we have something. And it's got a bunch of, again, these look like artifacts because there's something really large here, and there's a bunch of suspiciously vertical
Right.
blips.
So those are our sampling artifacts.
Yeah.
We've seen.
And so then I guess we could do the NUS
Yeah.
function, because we have this, the Fourier transform script, and we have the NUS script, which just does that. And I guess the only thing here is extrapolate. So because this is an NUS data, it should do the reconstruction, because obviously it has to interpolate data.
Yep.
And this is just telling us we also extrapolate out some more data, or if we just
That's
zero fill,
exactly right.
Right,
Yes.
let's keep it on. Which method should I choose?
Any one you like.
Yeah.
Actually, Maxent won't work for the 2D data. Like we have
Okay.
it for 2D.
All right, let's just keep it where it was.
Okay.
Now we update, and now let's execute NUS. There's a bunch of thresholds. I'm close. Done.
There it
And
is.
then Fourier transforms.
Beautiful.
Now it looks much nicer.
Yeah.
Yeah. Then we have this thing. I don't know what this is, but it's just because I'm a physicist and I don't know any chemistry.
Those are signals that are folded.
Yeah, that makes sense. Yeah, so now we have this, and that looks pretty good, and then we can change it to smile, and
Hey, Frank.
Yeah.
So the phase correction, let's say on the proton dimension, if I were to do, so let's say I correct it second time, the phase factor I see on the top, it has to be cumulatively added to what is already there in the P0 in the x-axis 1H panel, correct? Before I read it.
The interface will handle that automatically if you rephase an existing data set. It will compute what the new total phase is and adjust the processing script accordingly.
Right, because see, yeah, I guess I'm currently, it seems to be snapping to -16 at the middle, although it's hard to tell because it's only 16, but yeah.
Right, yeah.
So now this is not very far from 0 anyway, but yeah, this
Exactly.
goes out to, this goes out to -376 as opposed to -360, or, goes to 360 minus 16. So yeah, it's giving you plus or minus 360 around the existing value. That's good.
Exactly. So I think that's everything, and we're right at 5:45.